Okay, in this section we are going to discuss heat capacity of a system. So heat capacity is the amount of heat required to raise the temperature of a system through 1 degree Celsius, or we can say through. So this is the amount of heat required to raise the temperature of the system through 1 degree. So see, this definition do not mention the amount of or the quantity of substance we are taking. So if we are taking 1 gram of a substance and the amount of heat required to raise the temperature of 1 gram of substance through 1 degree is known as specific heat capacity. Specific heat capacity. So if we take 1 mole of a substance, 1 mole, then the heat capacity is known as molar heat capacity. Molar heat capacity. So here we can denote molar heat capacity by using the letter C. Let Q is the heat and the T is the temperature. So then molar heat capacity C is equal to Q divided by dt. Here Q is the amount of heat required. dt in the sense we are raising the temperature of the system from a lower temperature T1 to a higher temperature T2. Let us consider we are going to increase the temperature of the system from T1 to T2, and the amount of heat which we are required to increase the temperature from T1 to T2 is Q. So that is, we can specifically say C T1 T2 equal to Q divided by T2 minus T1. Instead of dt, we can specifically write that T2 minus T1. Actually, molar heat capacity C is C equal to dQ divided by dt. But the amount of heat transfer, during the reaction is very small. That is why they are simply using Q here. So actually, molar heat capacity equal to change in heat divided by change in temperature. That is dQ divided by dt. So if heat transfer is very less, we can write in this way also. Then the heat capacity at constant pressure, that is delta P equal to 0. So if we consider the enthalpy change of a system, it is delta H is equal to delta E plus P delta V. And first law of thermodynamics is, this is number 1, and first law of thermodynamics is delta E equal to Q plus W. This is equation number 2. And to calculate heat capacity, we have to know the Q value, right? So from equation number 2, we can write Q equal to delta E minus W. Here in this equation, we cannot cancel any term. Instead of writing W, we can write it as delta E minus P delta V. Okay, here minus and minus, so it will be equal to delta E plus P delta V. So Q equal to Q equal to delta E plus P delta V. This is number 3. So if we compare equation number 3 and equation number 1, the RHS side is equal. That is, here also delta E plus P delta V, and here also delta E plus P delta V. So this term is equal to delta H. Okay, that means we can write the heat capacity at constant pressure as Cp equal to Cp T1 T2. If we consider the temperature change as T1 and T2, then Cp T1 T2 equal to Q divided by T2 minus T1. This is equal to delta H divided by, here we can write it as delta T. So if we consider very small change, then Cp equal to dou H divided by dou T at constant pressure. So we can say heat capacity at constant pressure will be equal to the change in enthalpy divided by the change in temperature. Or we can say the heat capacity of a system of 1 mole of a substance, that is molar heat capacity, right? So molar heat capacity at constant pressure equal to the change in enthalpy of a system per change in temperature. In both the equations Cv and Cp, we wrote del Cv equal to del E divided by del T at the constant volume, and Cp is del H divided by del T at the constant pressure. So if change is very small, we usually use D, right? That is dE divided by dt. But instead of D, we are using del here. That is because we are differentiating the equation with respect to some variables, and by fixing some variables as constant. That is, here we are doing the partial derivation. Means at Cv means we are derivating the value of E with respect to T at constant V value. Now let's check the relation between Cv and Cp. So to find out the relation between Cp and Cv, I am going to take the enthalpy equation, which containing both E value, both E term and H term. So H equal to E plus PV. Okay, if I am going to take the smaller change, then I can write dH equal to dE plus T into PV. Right. So I am going to divide the equation throughout by the term dt. So if we dividing equation number 1 by dt, we will get dH divided by dt equal to dE divided by dt plus dPV divided by dt.